We're just going to review a little bit what we've done so far. Oh yeah, you need to borrow a calculator. So in chapter, let's see, 8.1 and 8.3. So 8.1 introduced a couple of formulas. I like that. Every math class needs a math interlude. You like this kind? Yes. You like this kind? We'll take whatever. Okay. All right. Did you put? Wait. Oh, you're good. So we talked about the whole idea behind this, but this is the formula that we actually sort of created, and I really, really, really hope that it makes some sense. You start at your best guess, and you improve on it by going up and down enough to catch so much data, so you're obviously that confident that your interval actually catches the real mean. Okay, just really want that to make sense. And this piece, what was this piece called again? Error. And by analyzing this by itself and solving for n, we got this equation. So now I can say, if I want to say I want to be this far off at most, how big of a sample do I need? Okay. I sometimes call this like a feasibility equation. What does feasibility mean? Do you guys know? Feasibility? If something's feasible? Anybody know? Feasible means, is it possible? Is it within my ability? Right? So a feasibility study would be, if that comes out to be 50, could we go talk to 50 people? Yes. If it comes out to be 358,000, okay, that might be not feasible for us, right? Okay, I like it. So this will tell you how big of a sample you need, and you can change the error to see how big of a sample you need. All right. Then we went to 8.3, and similarly, very nice analogy here, very nice mirror image. It talks about percentages in the same way. And we developed this formula. What do little hats mean? Does that mean they're like festive? They're Anybody remember little hat means on the P and the Q? So what's the little bar mean on the X? Sample. It's a mean, it's a sample mean. So a little hat on the P means it's a sample percentage. Okay, I like it. And again, for both of these, you'll be given just about everything, but you won't be given Z. What are you going to have to be told to be able to figure out what the Z score is?
P, Q, N. Okay.
What's that? I like somebody's drawing in the air for me. I have no idea. They have to tell you how confident you want to be, right? If I want to be really confident, Z's going to be big because I want to go way the hell out and catch a lot of shit. If I don't want to be that confident, I can go really small. I'll just go out and catch that much. Because if I want to be 95% confident, I've got to go far out enough to catch 95% of the stuff, right? That's why I don't know if I've used this analogy, I'm almost certain I have, but I don't like seafood, but I like the idea of throwing out a net. So if I want to be more certain that I catch a certain fish, I'm going to throw out a bigger net, yes? So I'm going to make my interval bigger, that's the bigger net, to catch the certain fish, which is the real mean or the real percentage. Okay. And then similar to this, we have the same kind of idea. Bang. And again, it would just be looking at this, setting it equal to E for the error, and then solving for N, some algebra. That's the little bit of algebra that sneaks into statistics. Okay, so you guys want to do a quick example of each?
Yeah.
Okay. All right. Somebody got all that written down? Oh, sorry. Go ahead. Here, I got to give you back some stuff. So Nina, let me know if all this here makes sense. There's a lot of.
It's gone a little bit. Thank you.
Sure. Okay, how we doing? We ready? You got this much?
This one's all like juicy.
Yeah. I don't know what's that. So let's do an example of the one I just raised. Let's say we take a sample and find a sample mean of 42. We know the population standard deviation is 10.8. Cool. Right. So we go somewhere, we know what the population standard deviation is, and we take a sample in this little area, and we get that sample mean. Right, so 42 is our best guess, but by itself, it's not enough information. I want to tell somebody, give them an interval that kind of captures how certain I am about this. So can we construct a 90% confidence interval? Somebody remember, I'm pretty sure did I talk about this symbol here? The little fish dude? Little fish dude?
Alpha?
Yes. What did that represent?
What area?
Area of the tails. I love it. And it's beautiful. It's the Greek letter A for area, and it's a fish with a freaking tail. The area and the freaking tails is just too awesome, right? Sometimes math people really pick a good thing. This is probably next. So this is the area and the tail or tails. So what would alpha be for this? If I'm making a 90% confidence interval, yeah, it's 10%, yes? You guys remember your little baby chart? Shit. Well, now that it's in my head, I'm going to share it with you. Little baby chart. On the z-score chart? Sorry. Now you're in my hell with me. Little baby chart. Do you guys see the 10%, the 0.10 confidence? What's the z-score that tells me? 1.645. You guys see that? But is Jeff going to be nice and give you one of those values? Not always. I will sometimes. I'll give you at least one problem where I want you to make a 94% confidence interval. Because I am an asshole. Okay. So, now I know Z is this. I've got everything I need. So I'm going to erase this here too. Yeah. So here's the formula again. Okay. And again, I want this to make a lot of sense. We did take a sample, yes. And they are talking about the sample mean, so therefore the formula, this part makes complete sense. Plus or minus makes sense, because I'm trying to go up and down so much to catch so much data. I don't know, this blue is not working too well, is it? So now you just plug and chug. Right? So I'm just going to put, what goes here?
42.
42, give or take. 1.645 steps. What was it? Oh, it didn't tell us what N was, did it? That would be good. Take a sample, let's say we take a sample of size. Why is this doubly important now? Why is it really important what this is? Not only do I need it for the formula, but what else is important?
It needs to be over 30.
Yes. I didn't say anywhere near that it was normal, but that's okay because my sample size is 41 and the distribution of all samples are 41, normal enough, yeah.
So what would we do if there was a sample size of 30 or less? Do we just not do normal?
Yeah, unless the problem, either they would say something like it's already normal or it's approximately normal to start with or something. I think there's one or two problems where they give like a sample size of 28. and they still want you to do the problem, but I would say just write down, assuming it was good to start with, then that would be, you know, I think there's one or two places where they make that mistake, but technically, we couldn't do shit. If they didn't say it was normal, they didn't say it was nice, and they gave you a sample size of 28, can't do shit in stats 1. Okay. Of course, that's all we offer here. Yes?
How did you get the Z-score again? Sorry.
Oh, all right, so 2 ways. Just in case, let's look at this. So if I want to be 90% confident, let's do it the long way, because you know I'm going to give you one that you can't do the shortcut. What percentage is down here? 90%, good.
Would it, if that's 0.90, would it be 0.05?
Good.
Okay.
Now, if you look up 0.05 in the negative side, right? Not as a z-score, remember it's an area. So what's the closest I can get to 0.05? It's going to be one of those
Oh, I see.
asterisk dudes. Yeah,
Okay.
there's your 1645. But the little shortcut is in the bottom right-hand corner of the positive side. But it only works with 3 confidence levels. You see that 0.90 is 1.645?
Yeah.
Kick ass. So don't forget your little baby charts down there. Oh, God, Jeff. I gotta come up with a better name for that. All right. So I highly recommend you figure out what this piece is first. So can somebody help me out with what that is?
2.7. How many decimals do we need to round? Is it
In this
like
case,
one more than?
Yeah, one more than what this is, so.
It's
yeah.
just
2 point,
2.8.
2.8? So you guys got it? Anybody else? A little verification? All right. And now you just do that, all right? You just subtract 2.8 from 42 and add 2.8 to 42. Out of there. Oh, well, let's do that. I'll normally give you some physical reality to this. This is just numbers, but it would be like ounces or something, right? So let me make that ounces. We're like weighing random rocks. Why not? Because you're bored. Are you done at this point? No. You get the best part of the problem. You got to write your little statement, right? I know. We are farmers. No, we are how confident?
90%.
90% confident that what?
That the average,
Nope.
that the mean,
Nope.
that
Sample
the
mean.
Interval. 39.2 ounces to 44.8 ounces. So we create an interval and we set it down and we say, we're such and so confident that the interval we just made actually catches or contains the population mean. So there's a population mean and we're trying to catch it. Do you guys get that? So there's a population mean. If I take a sample mean, are they going to be the same? I would put a lot of money that they're not the same. Yes? Because it's highly unlikely that a sample is going to be exactly the same as the mean, but it should be close. Yes? So we are such and so confident that this interval we created around the sample mean we got actually contains the real mean. That's basically what this is. So we are 90% confident that the interval we made, 39.2 ounces to 44, contains the true mean. I say true, I gotta start saying population mean weight of rocks. So we are such and so confident that our interval, blah, blah, contains the true mean or the true population, true mean or true percentage. Yes?
first started doing this, I put like, we are 90% can we put, we are 90% confident that the population mean weight of rocks is in the interval of 39.2?
And the answer is no, because that, all right, this seems really semantic, and it isn't, but it seems that way. But we don't create an interval, and then the mean kind of drops in or drops out. The mean doesn't just, we create an interval and then, it's coming, did we catch it? No, so the mean is sitting there, yes? Whatever I'm about to study, the mean exists already. And we either catch it or we don't. So it is really important that it's worded like this, because that actually represents what we're doing. We're making an interval and hoping our interval contains the real mean. We're not making an interval and hoping that the mean falls into our interval, right? I know it sounds the same, but it isn't. Okay, maybe. I know it's a little tricky. All right. Let's do an example of the percentage one, and then we're going to get into section 8.2. So everybody got that stuff? Okay. Let's say we talked to, oh, did I do that yet? Let's see. We created the, oh, that's right, we haven't done that yet. All right, before we do an example, this is coming back to it. We do have one thing to discuss. For means, n is greater than 30 to be normal, right? If it doesn't state it's normal, I need n greater than. If it says it's normal, how big of a sample do I need?
Anything.
Anything, it could be 1. That's chapter 6. We just had 1 in chapter 6. For percentages, that won't work. We need something else. Oh, this is what sucks. I don't think did I give you, damn it, I didn't bring it with me, I don't think. Do you guys remember, I'm pretty sure I gave you, there was a handout I gave you that had this big ass histogram for like flipping a coin. You guys remember that? So the situation was, I flipped a coin 14 times, and I wanted to count the number of heads I got.
From section, the first test, or like the second test?
The second test, but it would have been chapter 4 going into 5. But it's okay, we can work with this. If you do have the handout, it's good to look at, because this is a better drawing than what I just tried to do. But this is basically what it had. Does that look kind of normal?
Yeah.
Yes. Because what's the mean? What's the mean?
7.
7, of course, that's what we expect. It's n times p, right? I really want, okay. What's the lowest this could be? Considering this is the, 0, the number of heads I get after I toss it, flip it 14 times. What's the highest it could be?
14.
14. Okay. So isn't that nice? The mean is right in the middle. Shouldn't the mean be about where the highest peak is? And what will make it have the best chance to be normal is if the mean is somewhere in the middle. Because then it can go up and come back down. Just like it's going to go up, come back down, looking beautiful. So what happens? What if I had a coin that somebody had messed with?
It wouldn't be normal.
Maybe not. So what about a coin where the probability of getting a head was 0.01 and I flip it 14 times? What's the mean now? Fourteen times 1 is 14. 14 times 0.1 is 1.4. 14 times 0.01 is 0.14. Right? Or you don't have to make a weird X sound effect. You can. So mu NP is 0.14. So the tallest point, because that's the most expected thing, the tallest point will now be at 0.14. And what was the lowest this thing can go?
0.
Freaking 0. So here's 0, here's 14. For this coin, it's going to look like this. Does that have any chance to be normal? Hell no, it's hugging that damn wall. It has no room to go up and room to come back down. All right, so here's the, well, it's a long story too bad. Here's the medium story ending, right? NP has got to be at least 5. That will pull it away from this wall. Why is this sucker right on this wall? Because the mean was so damn small. So if n times p, if the mean is at least 5, then it's away from that wall, it's got room to come up, yes? Does that make visual sense? I mean, this is going to look like this. It ain't got no room to come up. This got room to come up. So even if this was at 5, it would still have room to come up and go back down. There's another wall over here, though, right? Yes?
If we get a problem and it's under 5, we don't do the problem?
Don't do the problem.
Okay.
I'm pretty sure they didn't make a mistake on that on the book. But I did point out there were a couple that they didn't have n greater than 30, so still got to do those. To be really honest, especially in a test, you still do the problem, right? Because there could be something you missed. I love it, my people that have the cojones to not do the problem when they're like, this ain't normal, I ain't doing it. I'm like, oh shit, that's a lot of points. You should still do it. I'm never going to give you a problem where some of you are going to waste time doing it and some of you are going to be like, I didn't have to do the problem. That would be so evil. I'm not there yet. I'm evil, just not that level. So here's the other thing. This is going to make it a little weird. This is the successes. The failures have to also be at least 5. And what that does visually is it pulls it away from that wall. So if I have, is everybody cool with it? 0 is the lowest and 14 is the highest. So if it's too close to this wall, it doesn't have enough room to go up. If it's too close to that wall, it doesn't have enough room to come down. So these together, this takes the place of n greater than 30. If I am dealing with a percentage problem, how do I know if it's normal enough? I have to check these two things. I like it. And now I'm remembering I don't have to make up the problem because we haven't done the other side of this yet, have we? Anybody need this handout from last time, the confidence intervals?
Yes.
Let's see. All right, so let's take a look at this. Okay, there. Should I put 1? Special view. Yeah. You can only control the sun.
Yeah, buddy.
Okay, that's good. Thanks. All right. Oh, that's the side we did. The one about the dolphins and all that kind of stuff. There's what we did last time.
Yeah.
Okay. So we need to do the other side now. Can you guys just see the percentage from the sample? I mean, what is the percentage from the sample that we've taken up there?
96.
No, that's how confident we want to be. What did we see in our sample that we took?
459.
out of
652.
bam, right? So that's how, and that's what x over n means. How many successes did we get? 459. Out of the total, 652. Okay, so somebody help me out. What is that correct to at least 3 decimal places? So p hat will always have to be at least 3 decimal places.
So
704? Is that what you guys got? Yeah. So what's Q hat gotta be then? P and Q are the same P and Q, even though they're wearing clothes. No matter what clothes they're wearing, they have to add to be 1. So what's Q hat gotta be? 296, I love it. And of course, what's N? Yeah, be careful, it's not the smaller number, it's the bigger number, total. So now you understand what I mean here. What do we have to check? Whether these have to come out to be?
5.
They have to come out to be at least 5. All right, so let's take a minute. N times P hat. Let me see if anybody notices a shortcut for this. So if you do 652 times 0.704, you're going to get 459, just about. Yes?
How'd you get Q?
Oh, whatever P is, Q is the opposite of that, so it's got to be the rest.
Oh, okay, so,
P and Q always have to add to 1.
okay, so
Yep.
you added 0.07.
So I did 1 minus, or somebody did 1 minus 0.704.
Oh, okay.
Yep. Does anyone get that? Do you get about 459? And why does it make sense? Because freaking, how do we get P hat? Did we do P hat x divided by n? So what's n times P hat? Freaking x, right? I don't know if you can see that. If you don't see that, who cares? You just do n times P hat, whatever the shit. But I already know from the beginning, 459. That's n times P hat. Is that bigger than 5? Yeah. 459. We're going to go by check. Now I gotta check n Q hat. That, of course, is going to be 190. I don't know, 193. Yeah. Okay.
Well, 192.992.
Gotcha. I was just trying. We're way this shit above 5, so we can round. And I know students are often like, "Oh, Jeff, you're always like at least 3 places, at least 4 places." All I need is more than 5. I mean, I don't have to be that specific in this case, right? Okay. So that takes the place of n greater than 30. So n greater than 30 is when I'm dealing with means. NP and Q stuff is when I'm dealing with percentages. Okay. So now we know we can do this problem. It's normal enough. How do I find the z-score?
You look at the little chart.
Can I use the, let's just call it little chart.
No.
Can I use the little chart? No, because what did your asshole teacher do? He wants you to do what kind of confidence interval? 96%. So can you do it? We got to do the old-fashioned way. Can you find the z-score for the 90? Can you draw a 96% confidence interval? And I need to find these z-scores. So to find this one, I need to know what area is below, and of course, what area is on that side of the chart of the distribution. What area is?
0.02.
Yes. There's 96% inside. There's got to be 4% outside. There's got to be 2% on that side. I really want this to make sense. Once I find one z-score, the other one is just the opposite sign because it's symmetric. It's on the other side. .02 is an area, not a z-score, so don't look for it as if it's a z-score. You have to look for it in the body. So I get pretty dang close to .02. Right? Yes. Good. So what z-score is that?
Negative 2.05.
Negative 2.05. What is that? So it's be positive 2.05. So in the formula, you just put 2.05. The negative and positive, certainly. They're already built into the formula, right? How you guys feeling right now? You guys all right out there? I mean, confidence intervals. We discussed the idea behind them, and they're probably one of the more recipe-ish things we do. I mean, it really is just find this stuff and throw it in the formula. They got to give you most of this. There's only a few things we got to calculate, and then we just throw it in. So what goes here?
0.704.
0.74, give or take this many. Standard deviations. What was it? 652. There. So there's your error piece. I would highly recommend you do that first. Push my calculator. That's a good question, Jeff. It's not supposed to be a good question. Uh-huh. Now look at, see how few parentheses I used? Now, if you have a calculator, older calculator that doesn't extend the square root symbol, you have that one parenthesis, do not close it until you're done putting stuff in the square root. If you have the square root button, the square root bar that keeps going, you don't need any parentheses. Thinking about that right there. For the error, right? So I need 0366. So now watch this. I don't know if I've shown you this yet. I'm going to store this. You don't have to do this. You don't have to do this at all. I'm going to store that. See a little store? I'm going to store that in X, and then I can just do 0.704 minus X and 0.704 plus X. Bam! Okay. This look bad. At this time of the day, I'm going a little loopy. All right. So then our interval is.
Wait, where did
from-
you find X on your calculator?
Oh, right there.
Oh,
So it's kind of cool. You don't have to do that, right? You can just do 0.704 minus 0.0366. That's a nifty little thing. So 0.667 up to 0.741. That's our interval. Let's zoom out here. Jeez. Okay. Now I brought ounces into that one problem. You got to get the units in there. So what the hell are the freaking units for a
People.
percentage problem? No, it's percentage. So just change your decimals to percentages, and that will count as units. So how do I word this conclusion? We are 96% confident that the interval, I like it. And now just make percentages. The interval 66.7 to 74.1% does what? doing means. This is all about percentages, right? So it contains the population percentage of what? Of who that did what?
That voted registered.
Yeah, of registered voters who voted in the last election. Whoosh. So we get a sample. So this is what's called inferential statistics. We want to infer something about the population from a sample we took. So that's going to inherently have a bit of a variation to it, because when we take a sample, it could be close, but it's probably off. So that's what this whole idea behind interval is trying to capture. It's kind of like, how off do we think we are? What's the chances that the percentage is actually not between there?
4%.
4%, I love it. We're 96% confidence in there, so we're 4% confident it ain't in there. Okay, I like it. Okay. And then, like I said earlier, this, if I do some algebra to this and I get n by itself, I end up with this formula. What is wrong, do you think? So number 2 is a totally different problem, right? So read through this. How many people would we need to survey to be within 3% of the true proportion of students who pass statistics the first time around at 99% confidence? I kind of give it away there with my parentheses statement, but do we know what Z is?
Not yet.
Not yet, but we can get it. Do we know what E is?
Yes.
Yes, what is it?
0.0366.
No, be careful. This does not have anything to do with the first problem. 2A is an error that I want to have. 3%, right? What seems to be like a decent keyword that will show up, not every time, but almost every time? Within. Isn't within kind of like the idea of the error? Give or take, I'm within this much, that's the error. So I know E is 0.03. What's the Z-score for 99%?
2.57.
Good. 2.575. So the only thing that I don't know was 2 things, and that's why I asked you that. The P hat and Q hat. We don't know what the shit those are. So what's always your best guess for a percentage if you have no idea? What's the percentage of people that like to eat broccoli over in the library right now?
0.
That might be a bad question, I don't know. What's the percentage of people in the library right now that identify as female? 50% is their best guess, yes? That's sort of like we can hash our bets and be kind of off by both sides, the least. Anyway, so when you don't know P hat and Q hat, you'll make it 50-50. Now here's the second thing. That wouldn't satisfy me because I'm a math geek. I'd like to know this instead. Do you think if we don't know something, this always sounds so weird when I say it, if we don't know something, shouldn't we be punished in a way in statistics? Does that make any sense? If we don't know something and we're trying to do something, shouldn't we kind of be punished? Shouldn't our interval get bigger or whatever if we're not sure about something? Does that make any sense? No? If there is a something that I don't know, shouldn't that somehow show up in my work? I mean, if I'm really not sure about what I see, shouldn't my interval kind of end up being bigger or something? That's what I'm calling punishing me. No? All right. So making these 50-50 will make n the biggest it could possibly be. So if I'm talking about how big of a sample do I need to make my error small, but I don't even know what P hat and Q hat are, I should have to take the biggest sample possible. So making P and Q hat 0.5 does that. So let's throw all this stuff in there.
And we're assuming that,
So again,
it's 50%.
50-50. We have to assume that because we don't know. So our best guess is 50-50. Oh my God. It's like 1800 something. $18.47. I don't know. Kind of lost track of my head. I have no idea. I get 1841.8 stuff, right? What's kind of sucky about that? This is this many of, this is 1841.8 what's? People! You want that last person, you gotta chop off an arm and say, I just need 80% of you. No, whenever we're talking about people, we always round up, right? So no matter what you get here, if it's a decimal, you round up. So I need 1842. Now, have you ever heard the phrase preliminary study? At all? Preliminary study? No? Okay. All right. Not knowing P hat and Q hat made N bigger than it had to be. Here, we did a preliminary study. Do we know what P hat is now? Do we have an estimate for P hat? From that sample we took.
Yes.
So it's the same problem as part A, but this time we did something. We did a little study. What's P hat?
0.738.
738?
Yeah.
So I don't have to guess it's 50-50. Now I know what it is. So what's Q hat?
0.262.
62. Cool. And now we do the exact same formula. We just don't put the guess. We put what we know. Holy crap. This time I get 1424 point stuff. So we need over 400 less people. That kind of is a big difference. Still kind of a lot though.
Excuse me?
Yes.
I'm still kind of tripping out on how the z-score is 2.575.
Oh, so it was 99% confidence, which means what's alpha? What's the area outside? If there's 99% inside?
So that would only be 1%, that would be,
Yeah.
okay.
But actually, in this case, I don't know why I keep coming up. Well, alpha's gonna become really big today. So I'm getting you ready for that. But this actually is even better. It doesn't have it according to alpha, it just says 0.99. There's 2575.
Okay.
Yeah. The other chart we're gonna use is gonna incorporate alpha. Oh, yeah. Okay. Now, so I don't know how you guys feel about that. Obviously, get in there and try the homework. It should be relatively what I call recipe-ish. All the concept went into developing the formulas. Now it's sort of like get stuff and throw it in. Get stuff and throw it in. Okay. Of course, the conceptual part of formulas is always when do you use which formula? That's always the hardest part. Now, kind of staying on the weird theme of punishment. What do you think should happen if? Oh, Smash, can you turn those back on? Thanks. What should happen to a confidence interval if we're not even sure what the population standard deviation is? Let's go back to my fish example, right? So you got this lake, and you want to catch a certain fish, and you're pretty sure it swims about this far, but you're not that sure. Shouldn't you throw out a little bit larger net because you don't know the variation in its swimming habits, right? Does that sort of make sense? I might be showing off how little I know about fishing. I don't care. I kind of like that analogy. So, if I don't know sigma, what do we do in general if we don't know sigma? We can take a sample and we can find the sample standard deviation, yes? Right? Is that the same as sigma? No. But is it an estimate for sigma? When does that estimate get better? When my sample gets bigger, right? Okay, I like it. So, what's going to happen is this. If we don't know sigma, we must use S. S is just an estimate for what the real standard deviation is. So it's sort of like that fish, I don't know exactly how far it swims, so I got to throw out a bigger net. I am going to be forced to make a larger confidence interval than normal. It's exactly like throwing out a bigger net. So what's going to happen is, this was the, if we know sigma, this is the formula. If we do not know sigma, all right, Jeff, there's a letter, there's another letter. There we go. We don't know sigma. We only know S. Here's what happens. It's still the same idea, but now we got to put an S here, because we're going to use it because that's our best estimate for what sigma is. And we're going to put a number here. And let's figure out, based on what we just said, let's figure out some properties of that number. The number we put here, how should it relate to what this number would have been? Based on what we just said. Is it going to be the same? Huh?
It should get bigger.
Exactly. One thing is, that number should always be bigger than the z-score would have been. Right? So if we would have used 2.575, in this problem we might have had to use 2.9 or something. What's going to happen to that number when the sample gets bigger and bigger?
It should get smaller.
It should get smaller. It should start to become this. Because when my sample gets really big, don't we basically say, well, then I know what this is? I mean, if my sample is really freaking huge, then I pretty much know my S is basically my sigma. Right? I don't know if you guys are with me. The bigger my sample gets, the better everything I find matches reality. Yes? So what we call this thing we put here, we call it a t-score. And what's funny is, does anyone know or even drink Guinness? Anyone drink any Guinness? You do? Yes. All right. Guinness, one of my favorite comedians said Guinness is like somebody took a beer and then put a whole turkey dinner into the beer. Yeah. It's like, whoa. So, there was a man who worked at Guinness. He did some analysis and he wanted to publish his findings, but Guinness was supposed to own everything that people that worked for them did. So he published it under a pseudonym. He called himself Student, and he just called it the Student's Tea Distribution. So that's a little bit of a story behind where this thing came from, right? You'd have to ask him, have a little seance, figure out why he called it the tea distribution. His name was William Gossett. So maybe just pick the last letter out. Okay. So I want you to realize all of your work is going to be exactly the same. The only difference is going to be you look up on the T-score chart instead of the Z-score chart. Okay. One little thing I want to talk about before I give you this chart, and we kind of just go over how the hell to use it. Do you guys remember, did we talk about degrees of freedom before?
It sounds familiar.
Degrees of freedom. Do you remember when the standard deviation formula, remember that a million years ago, where one was divided by n and the other was divided by n minus 1? Yes, maybe? So, just to do this again, let's see this. If I had 3 numbers that average to be 10, do you know anything about the 3 numbers? You know any of the individual numbers? If you only know they average to be 10, does any of them have to be 10?
No.
No. But what do they have to add? There's another puberty. What do we know they have to add to be?
30.
Because the average to be 10, you add them up, divide by 3, you get 10. It's got to be 30 then what they add to be. So can you just make up the first number? Yes. Give me a number.
18.
18. Somebody else give me another number.
29.
2. Sorry, he beat you up. So we didn't. Could those have been anything? It could have been anything, right? Could have been anything. Can I just make the third one up now?
No.
What's the third one got to be?
10.
Freaking 10, because we got 20 so far, right? That one has to be 10. So how much freedom did I have? Did I have all 3 places of freedom? No, I had 2 degrees of freedom. So degrees of freedom is n minus 1. So I really want this to make sense. What's so beautiful about this is when I get a sample mean, is it the same as the actual population mean? More than likely, will it be? No. I love it. Could you, like if I take a sample 4, 7, 11, right, and that's my sample. I really want this to make sense. Isn't there a last number that if I added it to my list, it would make the mean the same as the population mean? Isn't there a number that would do that?
Okay.
Didn't we just have it happen in our faces? Didn't we create a number that made this work? Yes? So what this is it kind of assumes that there is this number we don't know yet. So we know n minus 1 things. All right. That might be enough for that, Jeff. Okay. So let me give you this. And then let's talk about how the hell to use this. I know. Sorry.
This is A2, right?
A2, yeah. I'm sorry, my printer, of course, is starting to go inkless, so I've got some ink coming. So too bad, it's not in color. So let's see how to read this thing. So you can see why. Sorry, man. Thank you. We went over that degrees of freedom. If I wanted to create 95% confidence interval, what's alpha?
5%.
5%, and that's in 2 tails, yes? Can you guys see where it says 5% in 2 tails? Right? So it'll tell you which column to look at, yes? What if you would have made it one tail? What's in one tail if it's a 95% confidence? How much is in one tail?
2.5%.
Isn't that the same damn column? So you can't go wrong. Okay, somebody out there's like, it sounds like a challenge. All right, so what if I wanted to make a 95% confidence interval? They tell me it's normally distributed, still has to be normal, but I don't know sigma, right? So that means I have to use this. So 95% confidence. Jeff, you do this, yeah. So 95% confidence. And let's say n is 11. And sigma's unknown, but it is normal. And they have to tell me it's normal. Why do they have to tell me it's normal? Because, true, also specifically, n is not bigger than 30. All right, so what t-score would we use? We know we're looking at this middle column. Where am I going to stop? What's my degrees of freedom?
10.
10, I love it. So that would be the value I would put where I would normally put a z-score. I'm going to put that. You guys kind of with me on how to read this? So if I wanted a 98% confidence interval, which column would I look at? 98%.
The second one.
Second column. Alpha would be 0.02. It's 2% and 2 tails. Bam. Now, real quick. Right now, we have no idea why the hell this thing says 1 tail and 2 tails, correct? You guys with me? It's kind of like, why did they do that extra shit? That's going to be chapter 9. We're going to be doing claims like we can raise your average SAT score. We can raise the average SAT score, which would be a 1 tail thing because they only want to see above. Does that sort of make sense? It's a little bit, that's in our future. But there's a really, really good reason why it's 1 and 2. Confidence intervals always make 2 tails. Right? When I chop it, bam, I made 2 tails. Okay. So let me give you this then. Let's see if you can do some lightning round. So let me ask you, why were t-scores invented? Why were they invented? For what situation?
When you don't know S, or when you don't know sigma.
Yeah. So when am I going to use t-scores?
When you don't know sigma.
Yeah, well, you know, this thing is crazy. All right. You guys have enough light out there? You guys are good? Oh, don't worry, that's okay. I think they're okay. I'll let you have eyes on there. Alright, so you see how this thing works? It's a t-score lightning run. So assume we have a normal distribution, we only have S, we don't know sigma. So try to do the first two. The third one we'll talk about. We'll see if you guys can figure out. There's a little something with the third one up there. Let me pop one of these. I'm gonna pop me out my later. All right, let's see. What's the degrees of freedom on this first one here?
21.
One. Oh, you're looking at number 2. Looking
Oh,
at
I'm
number-
sorry.
Oh yeah, this hand was pointing here, but it's just sitting. So I got degrees of freedom of 5. What column am I gonna look in?
The first.
Good, because I got 1% outside for 99% confidence. And then I just stop at 5, and there it is. 4.032. Which is way bigger than any Z we normally use. So it kind of makes sense, the smaller the sample, the bigger, I mean, that t-score's got to really cover our ass for not knowing something, the smaller our sample gets. This isn't too bad, right? Degrees of freedom here?
100.
100? 90%, so what column am I looking in?
Fourth.
The fourth one, because that's got 10% outside. And then I just stop at 100. There we go. 1.66 out. Yeah. Now what's a little bit different about part C? I know the degrees of freedom is 92, but yeah, Jeff's sucky little chart doesn't have a 92 on it, so. It's this general theme in statistics. The less you know, the more you gotta, I gotta figure out another way to say it. It's more you gotta punish yourself, so. I'm gonna make my t-score bigger, so if I don't have it on the chart, I'm always gonna go to the next degree of freedom below it. So I'm not gonna go 92, I'm gonna go 90, which is gonna make my t-score bigger. So if I look at 90, and what column am I looking in for 98%? Yeah, the second one. And I just stop at 90. Yeah. 2.368.
Wait, why 0.02 and not 0.10?
Let me see. I might have misread it. Does it say 98? Yeah, it says 98% confidence. Right.
Oh, okay, then why are we taking 92 and making it 90?
Oh, that. Because 92 is not on the chart.
Oh, okay.
Yeah.
So you wanna, what if
So
it's
you
like 90?
always take it to the next one down.
So if it's 94,
You take it to 90.
okay.
If it was 99, take it to 90. Now, you know, if it's 99, I'm not going to be that strict on that. But again, it's the whole idea of, to be honest, if there's something you don't know, you kind of make things a little worse for yourself when you're doing a statistical study. Somebody had their hand up. Everybody good?
They answered my question.
Oh, you good? Okay. There's something I wanted to say. Oh, there it is. Okay. Now watch this real quick. Pick any column. Let's pick this middle one. What is happening to the t-score?
It's getting smaller.
Sorry. So as I move down the chart, it's getting smaller. And in fact, what happens when our sample gets large? What do these look like?
Regular.
Don't they look like normal stuff? Now this was 2575, right? But this chart tells us, it was kind of close, but it's actually 2576, so that's fine. But, so, isn't that what we just said earlier? T-scores have to always be bigger than Z-scores, but they will approach a Z-score when sample gets big. Because what's happening when a sample gets really big? How are we feeling about S? We're feeling better and better. It's a better and better estimate. So I need this thing less and less. So if I have a really, anybody else intrigued by what the shit that is? Nobody? Have you ever seen that on math? You know, here's the technical thing. When your sample size is large. All right, what's large? Yes, anybody else have that question? What is large? It depends on the situation. That's why they just leave it vague, right? But already at like 2,000, it's pretty damn close, yes? Okay. So it really depends on the situation. All right, so what about number 2 here? Now we're getting a little more technical, not just can you use the chart, but can you think about what you're given?
So would we go back to the Z-score chart?
Maybe. In some of these, the right answer is a z-score. In some of these, the right answer is t-score. And one of these, the right answer is can't do shit. Can anybody identify Shivas? Can anyone identify, there it is. Which one we can't do?
C,
Yeah, what's wrong with C?
not normal, and it's.
Yeah, not only is the population not normal to start with, does the sample size save us?
No.
Nope. So, cannot do this.
Is that because it's below 30?
Yep. So if it's below 30, they have to either tell us it was normal to start with, in which case the sample size doesn't matter because it's normal, or the sample size has got to be greater than 30, and we're screwed here. All right, so do the other three real quick, A, B, and D. C's answer is no can do. Yeah.
Real quick, so if the sample size is exactly at 30, it's normal, or does it have to be greater than 30?
Technically, it's got to be greater than 30.
Okay.
Yeah.
So it wants you to find the D-score and T-score?
Yeah, well, it wants you to either, I want you to first say what to use, if anything, and then find the score, yeah. So on part A, is it a Z or a T?
Z,
Why?
is it sigma?
Yeah, good, that's it. Once we know it's normal, either they say it or the sample size is big enough, the only thing that determines between the two is which standard deviation do we know. And be really careful, I want to say this, in the book, and just like in real life, if I know sigma and I go take a sample, can't I calculate S if I wanted to? I got a sample, I can calculate S, can't I? Would I use that if I knew sigma?
No.
No. I love you guys. Some of you guys don't even like use words, man. So if I know the actual population standard deviation, I can calculate S. Of course I can. I can put that shit in 1-bar stats and get S all day long. Why the hell would I use it if I knew sigma? Does that make any sense? So in your homework, there's going to be a couple problems, I think, that you know both. Don't use S if you know sigma. Don't. You can use Z-scores then. Okay, so part A definitely can use a Z-score. So I don't have to worry about degrees of freedom. Gather. So I want to be 90% confident. Now here's something neat. I'm going to use this chart to look it up. Is everybody cool with that? Because these scores are at the bottom. So which column am I looking at for 90%?
0.10.
Yeah, and if I look all the way to the bottom, I get 1.045.
How'd you get 1.645 when you,
For what, sorry?
how'd you get 1.645?
So you told me this is the fourth column, right?
Yeah.
We go all the way to the bottom. Why do I go all the way to the bottom? Because if I stop, I get a T-score. If we go all the way to the bottom, I get the Z-score.
Okay.
Yeah. Because T-scores become Z-scores when the sample is large. right? So if you stop, you get a t-score. If you go all the way to the bottom, you get a z-score. What about part B? Why is it okay? It says population not normal.
So it's greater than 30.
Oh, yeah, sure. So which score do I need to use? I only know S, I don't know sigma. So I've got to use a t-score. So now I have to know degrees of freedom. Because I have to stop somewhere. What's my degrees of freedom?
38.
38. Which column am I going to use
30.
for 98%?
Oh, second.
I get a second. And then I stop at 38, 30. 2429. This one was nope. And then this one, it's like double good. Look at this shit. It's normal already and it's big enough. Damn. But what do I use?
60.
No. I mean, T or Z.
Oh, T-score.
Yeah, I only know S. I don't care that it's so beautiful. I only know S, so I gotta use the t-score. 99%, what's my degrees of freedom? You already told me it was
60.
And I want a 99%, so which column am I looking in?
First.
Yeah, the one with 1% outside. And my degrees of freedom is 60. So I get 2660. Right, 2660. Of course, my math geeky mind loves that there's a 1660 and there's a 2660. Yeah. Okay, sorry. And now, finally, oh my gosh. For everybody who's missed having a sample of data to actually work with, here we go, now we can do it. Because now that we understand t-scores, we can handle if we only know S, and we can calculate S, right? Let's see if everybody remembers how the hell to do it. 1 bar stats in your calculator. Can you guys calculate the mean, the sample mean and the standard deviation? Oops. What do you guys get? Anybody got the mean yet? So you put your data into list 1. Then you do stat count 1 bar stats. Make sure it's list 1. This is what I get here. Say like 78 point, don't say, let's just go out a couple places. 29. What's my standard deviation? Let's see if you guys understand the discussion I had earlier and how it doesn't relate here. What standard deviation do I use? So what was it we put into the calculator? Where'd that data come from? The data that we put in came from where? A sample. So the calculator, and I told you this like a long time ago when we first did this, calculator is going to do both because it has no freaking idea if I put a population into it. We put a sample into it, so what do we have to use? S. It's a sample that we put in there, right? The calculator doesn't magically know what the population is. There's no way it can. It gives us both because we're the humans. We're supposed to know what we're doing. We know we put a sample in there, so we know we have to use S. this formula, what do we have to figure out? What's n?
7.
7. So we know n, we know s, we know x bar, of course we still need t, but they told us 98% confidence, and of course what's the degrees of freedom? 6. I like it. So 98% confidence, which column are we looking at? For 98% confidence?
Second.
Yeah, it's gotta be the one that's got 2%, and then I just stop at 6. So it's like 3143. So now the formula is gonna be x bar, give or take, this many standard deviations. What was 7? So the amount of work is the same, it's just I'm using one chart or the other. So if you do your error first, I get 18.679. How? Okay.
That's 679.
18,679, yeah.
That's 674.
3.143,
Yeah.
15.724.
Oh,
So then I would do 78.29 minus that. 78.29 plus that, and I get 59.61 up to 96.97. Oh my God. Now this, is this something, what do you guys think about that? Is that good, is that useful information? What is that trying to capture? What is it we're talking about?
The true mean grade.
Grade. So what range is that? The true mean grade is anywhere from an F to an A. Is that useful?
No,
Why is it so bad?
because 98%, I don't know.
That's one thing. 98's a little bit more than 95, so that pushes it out. But the really bad thing is we only used 7 data points. Very small sample, so we're really, really not sure about what we found. So we can see that in the confidence interval. We're really not sure and look at the confidence interval like crazy. Okay, maybe. So you know we gotta do, we are 98% confident that the interval 59.6 to 96.97, whatever, contains, there's no real units on grades, contains the true mean grade, whatever this is from. We're 90% confident that the interval blah to blah contains the true mean grade. And so effectively that's shite. You probably have to go back and take a larger sample.
It's basically the same thing as 8.1, but like just with different
That's what I'm saying.
scores.
It's the same exact work. You just look at one chart or the other chart. And in fact, we're going to be using the t-score chart a lot now because the z-scores are on there too. I would only use the z-score chart if I gave you a 93% confidence interval, which you know I will give you something like that. Okay. Yes?
Z-score is only where it says large, right?
Yeah, if I'm using a t-score chart, z-scores live where it says large. Yeah, because t-scores slowly become z-scores because they become less necessary the bigger my sample gets. All right. I don't know how you feel about this. I would let you out early a few times. Let's get out. Let's go. We can end now. So next time we'll get into chapter 9. Yes, we will.